Okay, I think it's time and we should get started. So this class, we're going to try to finish up all the contents regarding the mass and energy balance, right? So I saw that, actually, I should say that most of you have gone over the contents for our last class. Right, so last class is mainly an introduction of all the reactors that we're going to use, right? So again, regarding the reading assignments, it's going to be the chapter 4 of the textbook. Again, I want to reiterate that I would say this is the most important chapter of the entire class, because later on you can find that for a lot of the design for the engineering devices, we need to use the mass balance. I'll keep mentioning the mass balance when we solve these problems. Right. So if we do a quick recap, so last class we introduced the general mass balance equation, right? So just to test whether you, let's see. Well, it seems that my mouse is not working. Okay, then we can just skip it for now, all right? So basically, the equation for the mass balance test is that we can equate several terms for the operation of a control volume, right? Okay, I think it works now. Let's see. It's very weird. Okay. Well, let's just continue. Okay, I won't keep trying that. So we can list several simple terms regarding the flow or regarding the balance of certain mass species for a control volume, right? So we have basically the accumulation term equals the inflow or the in term minus the out term minus the reaction term, right? So this is the general equation for the mass balance. So if we represent it in a more mathematical way, and this is the part that I didn't introduce in our last class, is that we can show each term in a little bit more complicated expression, which is V multiplied by dC dt equal to Q in multiplied by C in minus Q out multiplied by C out minus V multiplied by R. Okay. So basically the accumulation term, can be represented as the change of the concentration for this species in the control volume multiplied by the entire volume of this control volume, right? So we're talking about the accumulation of the entire mass, not the accumulation of the concentration, right? So we're talking about basically, let's say if there are some pollutants, right, organic pollutants. So we're talking about the entire mass of these organic pollutants in this reactor here, right? So that's going to be equal to the inflow of this organic pollutant minus the outflow of the organic pollutant and minus the reaction or the amount that's being reacted, okay? So why do we list it in this way? So first, what we can do is we can check whether the units is conserved on the left-hand side and right-hand side. So if you check their units one by one, okay, so for the accumulation term, we know that volume has the unit of meters cubed, right? And then the concentration has the unit of mole per meter cubed. And then you further divide that by time. So you have a second term here, right? So basically this means that it's going to be mole per second. Okay, so this is the basically the accumulated amount for this organic pollutant. And that's shown in the entire number of moles per second or per unit of time. So if you further check the unit for the right-hand side terms, then the Q in or the flow rate has the unit of meters cubed per second, right? And then the concentration has the unit of mole per meter cubed. So which means that this term is also going to have the unit of mole per second. Okay, so the same for this term here. And then finally, regarding the reaction term, then it's going to be mole or the meters cubed. And the reaction rate is mole per meters cubed per second. Okay, so what this means is that the unit is also going to be mole per second. Okay, so that's why we always need to pay attention that whenever we list out this mathematical equation, we need to include the volume term for the accumulation term and the reaction term. Okay. So one thing that I also point out is because there's a restriction regarding the reaction term, where the R has the unit of mole per meters cubed per second. Okay, so what this means is for a first-order reaction, where R is equal to K multiplied C, right? So which means that this K multiplied by C is also going to have this unit. So we know that the C has a unit of mole per meter cubed, right? So what that means is the K is going to have a unit of 1 per second, all right? So that's why for first order reactions, the reaction rate constant or the reaction rate coefficient are going to bear a unit of inverse of time, okay? So this is basically trying to show that whether the units are going to get conserved for this mass balance equation. So we further introduced several simple examples regarding the mass balance. So first we started with the cases that do not have reactions. Okay, so for the case that don't have reaction, we just have accumulation equal to in minus out. Okay, so first we talked about this primary clarifier where you just have the sedimentation of the pollutants, right? So we further introduced the removal efficiency, this concept, which is basically C out minus C in divided by C in, right? So this is the removal efficiency for certain pollutants within this water treatment or wastewater treatment device. Okay, so the second example is further simplified, which is the physical mixing, and we introduced the concept of steady state. So what steady state means is that the accumulation term is equal to 0. Okay, so if accumulation term is equal to 0, then what that means is the in is just equal to out. Okay, so that will get things further simplified, and we introduced the mixing of the sewage water. So basically the snow melt with the stream water, right? So we have let's say a snow melt that has certain high concentration of the salt, and then we have the stream water which has very low concentration of the pollutant, and then this is going to give us so basically based on this concept, we can calculate what is the concentration of the pollutant within the mixed water, right? So this is the examples that do not involve reactions. So these processes are very simple, right? But we know that for most of the treatment for the water or the wastewater, there has to be some reactions getting involved, right? So when there is a reaction term, right, we cannot ignore this term anymore, right? So we mentioned that if we want to consider the reaction, there are two things that we need to pay attention to. One is the reaction kinetics. So we went over this concept in our last week's lecture, right? So we mentioned that there are reactions that can have different orders. There can be zeroth order, first order, and second order, right? And we mentioned that the first order reaction is the most common one, which has the relationship of K equal to, or R equal to K multiplied by C. Basically, the reaction rate is proportional to the concentration of this species. And we also mentioned that we need to pay attention to the reactor type, right? So there can be all different types of reactors being involved in this environmental engineering process. So there are mainly three major types. So one is called the batch reactor or the completely mixed batch reactor, CMBR, which is the preferred name in your textbook. So there is a reactor type called the continuously stirred tank reactor, the CSTR, or the textbook also called as, I think, CMFR. Okay, so continuously mixed flow reactor, right? So the final one is the plug flow reactor, or the PFR. Right? So these are the three major types of the reactors, and we're going to do some practice of them one by one. So first we have to know how they're being operated. What are the major features for these reactors? So last class, I think we stopped at the batch reactor, so we can maybe further introduce it a little bit, right? So one thing I also want to mention is that from now on, we're going to deal with first order reaction for most of the time. Okay, so you just need to memorize this reaction rate equation here. Okay, so the batch reactor, as I said, is also called as the CMBR, the continuously mixed batch reactor in the textbook. So what happens for the batch reactor is that, as the name suggests, so everything or all the reaction happens in batches, right? So you can imagine there's a reactor that looks like this, right? So I think the schematics here is going to be more straightforward in understanding. So basically we have a cylindrical reactor or whatever shape it can be, right? So what happens is we'll first introduce the influent into the reactor. So this can be wastewater, right? Contains some organic, again, some organic pollutants. So they're first poured into this reactor here. And then what happens is we're going to use a stirrer to keep it well mixed, okay? So at the same time, we're going to add some reactants into this batch reactor to let it react. So to basically let this organic pollutant concentration to reduce, right? So after a certain amount of time, okay, after a certain amount of time, then basically we can monitor the concentration of the pollutant. If the concentration is low enough, we can send it to the effluent. Basically, we can discharge it, right? So we can use this method actually to reduce the concentration of the pollutants in the wastewater, right? So if we want to calculate how does the temperature change as a function of time, then we need to use the mass balance equation again, right? So we have the accumulation term equal to in term minus out term minus reaction term. But what we're trying to solve is the process that's just happening in here, okay? So at this stage, there's no inflow or outflow. So this is just pure reaction of this pollutant here, right? So what that means is we don't have these two terms. These are going to be equal to 0, right? So basically you just have accumulation term equals the negative of the reaction term. So further, if we plug in the mathematical equations for these terms, right, we have, if you just scroll up, right, in here, if you check this mathematical expression, we have the accumulation term equal to V multiplied by dC dt, and then the reaction term is minus V multiplied by R, right? So if we just write it out here, this is the mass balance equation for the batch reactor. So further, you see that we have volume on both sides, right? So we can cancel the volume because we know that volume is always a positive value, right? So we can cancel it, right? And further, since we have the assumption that this reaction is first order reaction, dC dt is going to be negative of Kc, right? So this is the basically how the concentration is going to change as a function of time. And further, by integrating this equation, you can know that, so first dC divided by C is going to be minus K dt, right? And then you do the integration on both sides, right? So final answer will have this type of expression where basically the concentration of the pollutant within the tank is going to be an exponential term, or it's going to have an exponential decrease as a function of time, right? So if we plot it out, this is time, this is concentration of the pollutant, right? It's going to decrease exponentially, which is actually quite effective, right? So if you, for anything, if there's an exponential decrease, then we're happy about it because what that means is the concentration is going to decrease quite rapidly from this process, right? But actually, if you go to the industrial plant, if you deal with the real environmental engineering devices, so people never use these batch reactors, right? So there are some critical disadvantages with these type of reactors or the batch reactor. So as I have suggested here, you can see that there's no in or outflow. Okay, so this is a critical problem for this reactor, mainly because let's say if we're trying to build a wastewater treatment plant for Rolla, okay, so Rolla, we know that there are residential areas, there are industrial areas, and there are farmlands nearby, right? So all of these are going to generate wastewater. And although for each household, the generation of the wastewater is intermittent, let's say if we plot the flow rate for each household, right? So say, so household 1, right? Household 2, and then so on and so forth, because there are so many sources, right? And you can also have the industrial emission of the wastewater. Although for each household, there can be intermittent discharge of the wastewater, right? Coming out of your toilet, coming out of your sink, right? So, but because there are so many households and also so many industrial processes, so if you plot out the generation of all the wastewater, okay, so they're going to show a continuous trend here. So it's not intermittent. But the problem for the batch reactor is that it can only react intermittently. Okay, so you have to pour in the wastewater and then let it react and then discharge it. Pour in, let it react and discharge it. So you cannot. So what happens is that you cannot tell these households or industrial plants that let's wait for some time. My batch reactor is reacting, right? So you cannot push their wastewater back. So that's why we have to use some devices that can introduce flow and discharge flow at the same time. So the batch reactor has the disadvantage that it cannot react continuously, okay? So we have to use some flow reactors. Okay, so that's why we need to use the CSTR and PFR. Okay, so but before we introduce these two other types of reactors, we can do a simple practice in here to just see how we can apply our knowledge of the batch reactor to water treatment. Okay, so maybe let's spend 1 minute to look at this problem here. So this is an example problem in your textbook, actually after the chapter, right? So you can spend 1 minute to read the question here. Okay, so let's take a look at this problem, right? So this is talking about a water tower, right? So It's talking about replacing or doing some fixing about a water tower to install some devices. Okay, so if we just draw a simple water tower, right? So you have the tank at the top, right? And there are some water inside, right? So we know that this water tower contains certain volume of water, which is 4,000 meters cubed, right? Okay, so so I saw someone ask a question here. I'll explain it later on. So that's a good question. All right. So what this problem tells us is that you can treat it as a completely mixed batch reactor, or for simplification, it's a batch reactor, right? And then what happens is that people have isolated this water tower, right? So theoretically, there is water going up or going down, but to install this device, they just cut this flow from the water tower. All right. So this has been taken out of service to install the chlorine monitor, and the concentration of the chlorine in the water was 2 milligram per liter. Right. So we know that the concentration at the beginning is 2 milligram per liter. So there's a reason why we add chlorine in the water, right? That's for disinfection, because for drinking water, there are some bacterial viruses inside. So we have to inject these chlorine into the water to disinfect them, right? And then because it has to be taken out of service, right, for a time period of 8 hours, right? Since the chlorine in the water is going to react, so basically the chlorine in the water is not stable. It can get vaporized, right? It can also get reacted with the existing species in the water. So for this reaction, it assumes that it follows the first order reaction kinetics, and then you have a rate constant of 1 per day. Okay, so again, pay attention to this unit here. As we mentioned, the reaction rate constant has to carry a unit of 1 per time, right? 1 per second, 1 per hour, or 1 per day. Okay, so the question is asking us, what is the mass of the chlorine, or basically, what is the chlorine concentration when the tank is put back in service after 8 hours? Okay, so it's asking us to solve for the concentration of the chlorine after a certain amount of time, right? So if we know that it's a batch reactor, we can just plug in the equation. C is equal to C0 exponential minus KT, right? So we know that C0 is 2 milligram per liter, right? K is 1 per day, right? And T is 8 hours. Okay, I saw that Clinton asked the question whether we have to change the unit, right? We have to change the unit because you cannot simply multiply 8 by 1, right? The time here will not get canceled. Okay, so what that means is that we have to convert 8 hours into 1/3 days, right? Because each day has 24 hours, right? So what that means is we can just plug in all the values here, multiply by the exponential of minus 1 multiplied by 1/3, right? And you can find out that the final answer is 1.43 milligram per liter. Okay, so this is the concentration of the chlorine after 8 hours, right? Because it's going to decay or it's going to react within the tank. So the second part of the question was asking, because we don't want to waste this water, right? We cannot directly dump them because we can still use them, right? So what people can do is we can inject chlorine back into the water to raise up the concentration of the chlorine, right? So it's asking us, what is the mass of the chlorine that must be added into the tank to raise the chlorine level back to 2 milligram per liter? Okay, so this is just a simple calculation of what is the mass needed to change the certain species concentration to a certain level, right? So we can list out the equation. So the mass is going to be the change of the concentration, delta C, multiplied by the volume, right? So the change of the concentration is 2 minus 1.43, right? Because we want to change it to 2 milligram per liter, right? So we also need to bear in mind is that this has a unit of milligram per liter, right? So we need to multiply the volume, which is 4,000, right? But this has a unit of meter cubed, right? So what this means is that we need to convert everything into the same unit, right? So basically, this is going to be 0.57 milligram per liter multiplied by 4,000, and then multiplied by another 1,000 that has a unit of liters, right? So by multiplying all of these together, you can find that the final answer should be 2280 grams or 2.28 kilograms of the chlorine. Okay, so this is a simple application of this batch reactor problem here, right? So as we said, the batch reactor has a critical issue because for water treatment, because it doesn't have inflow or outflow, but for the treatment of the water, there's always flow going by, right? So that's why we need to introduce the flow reactors. And the first one that we can think about is the CSTR. So the CSTR, the concept is very simple. So what happens is, you remember here we have the batch reactor, right? So what about we just dig 2 holes, right? So we introduce the flow in here, we discharge the flow from here, and then we still let it mix inside the reactor, right? So that's doable because we can basically introduce the untreated water into the tank, let it react, and then discharge the reacted water. So everything is in a flow condition, right? So we don't need to worry about letting it happen in batches. All right. So we still have the assumption that everything is well mixed within the tank, right? So basically, this is the concept for the CSTR, the CMFR. Okay, so you see, basically, this is a schematic diagram of this device, right? You have inflow, you have outflow, and you have the completely mixed condition within the tank, right? So for the CSTR, very important, there are basically 2 very important assumptions we make for this reactor. So the first one is we assume that it happens at steady state. Okay, so if you recall, the definition for steady state is that the accumulation term is equal to 0, right? So that will simplify our mass balance equation a little bit because now you just have in minus out minus reaction equal to 0, right? So if you basically use this entire tank as a control volume, right? You can first have this reaction, first have this equation here. And then you can start to plug in the mathematical terms, right? So the in is going to be C in, Q in, minus C out, Q out, minus V multiplied by Kc equal to 0. Okay, so this is a term for the reaction term. We're assuming this is first order reaction. Okay, so then we can make some simplification for this reaction, for this equation, right? So we know that there's only 1 inlet and 1 outlet. Okay, so because of the mass balance for the flow, then Q in is going to be equal to Q out, right? So we don't need to write these subscripts anymore. So everything will just simplify into Q. And basically, this is the equation that we have here. Okay. So then one thing we can do is we can divide everything by Q. Okay. So what we're going to have is C in is going to be equal to C out plus V divided by Q multiplied by QC. Okay. So if you look at these concentration terms here, right? So we have the concentration of the pollutant into the tank. We have the concentration of the pollutant out of the tank. And here, this C here is actually the concentration in the tank, right? So basically we have C in here, we have C out here, and we have C in here, right? So then it comes the second most important assumption for the CSTR is that we assume C is equal to C out. Okay, so this is the assumption we make for the CSTR. So the first one is we assume that this is under steady state. The second one is that C is equal to C out, right? Which kind of makes sense because if everything is well mixed, then the concentration at the outlet should be equal to the concentration or should be close to the concentration of the species within the tank. But I would say this is still a too idealized assumption, right? We know that it's not going to be in that way. So let's say if the organic pollutant has a very high concentration at the inlet, let's say 100 milligram per liter, okay? So outlet concentration, let's say is 10 milligram per liter. Then certainly at a location that's close to the inlet, it's not going to jump directly down to 10 milligram per liter, right? It's going to decrease maybe abruptly, but not suddenly, right? So that's why this is a very important assumption, although it's not a very real assumption here, but it's going to help us solve the concentration or basically solve the performance of this CSTR here. So then it's going to get simplified, right? So we just write C out in this equation here. And then further we make a substitute. So what we do is we assume that theta is equal to V divided by Q. Okay, so basically we want to substitute this term here. So what happens is we can basically change this equation to this equation. Let me just draw an arrow here. Okay, so we have C in equals to C out plus K C out multiplied by theta. And then regarding the performance of this CSTR, people are interested in what is the concentration outside, right? So we don't know where how this reactor performs. We really want to know what is the concentration of the organic pollutants that's being discharged, right? So that's why we can solve for C out because you have these terms on the right-hand side, right? You can solve it. And this is the equation that's relating the concentration of the species at the outlet of the CSTR and then at the inlet of the CSTR. Okay. So that's going to be C in divided by 1 plus K theta, right? So actually, I want to say that this is a quite interesting phenomenon because if you see, the CSTR is simply a batch reactor that has two holes in it, right? And for a batch reactor, you see the concentration, basically, for the batch reactor, you see the concentration is decreasing exponentially with time, right? You have a sudden drop here. But for the CSTR, it seems that this exponential relationship has changed to a linear relationship, right? You don't involve these exponential terms anymore. Everything is just linear, right? And then another thing I want to point out is that you see this theta term that we defined, right? So if you check the unit for it, which is meters cubed for volume, divided by the flow rate, is meters cubed per second. And you're going to have a unit of second. You have a unit of time, right? So this also makes sense because if you check the K theta here, so we mentioned that the K has a unit of 1 per second, right? And then the 1 here doesn't have any unit, right? Which means that the theta has a unit of second, right? So basically, you can find that for this substitution, we define a new term that has a unit of time. And people actually define this V divided by theta term sometimes as the characteristic time. Okay, so the characteristic time of the CSTR of this reactor here, right? So we want to mention that basically we changed from a batch reactor to the CSTR, but we also completely changed the concentration at the outlet of the reactor, right? So one is an exponential term and one is just a linear term. So now we can do another practice for this CSTR here, right? So I'm showing this problem here, right? So we can spend maybe another minute to look at this problem, right? To just practice this calculation here. So our time is up, right? So what this problem is trying to say is that in the water treatment or the wastewater treatment, sometimes what people do is we can designate a certain water body, let's say a small lake, a small pond, to first let it process the wastewater coming out of the household or industries before we discharge them into the lake or into the river. So let's say if this is the Mississippi River, right? We know that there are some wastewater discharge, right? So we can designate a small lake to just process these wastewater first before we send them into the river, right? And within this lake here, we can probably introduce some bacteria inside. So we know that bacteria can degrade the organic waste within the wastewater, right? So this problem is talking about such a system, right? So we're talking about a sewage lagoon, right? A small pond that has certain surface area and certain depths, okay? So it has 10 hectares. So 1 hectare is basically 10,000 meters squared, right? See, this is a very large area of the lagoon here, right? And it is receiving certain amount of water or the sewage, basically the wastewater, right? And it contains certain concentration of this degradable contaminant, right? So we can basically write out or draw a schematic diagram for this small pond here. Okay, so let's say this is our sewage lagoon, right? We have inflow, which contains certain high concentration of this contaminant. Right? We know the flow rate is equal to 8640 meters cubed per day, right? And then the concentration in is equal to 100 milligram per liter, okay? And then within this small pond here, you see that first it gives the assumption that it is under steady state, right? We know it is the first assumption that we make for the CSTR. And then the second assumption is that it's assuming that this is well mixed. Okay, so it satisfies both of the assumptions. Let's just draw a stirrer here to make sure that this is a CSTR, right? And it says that the concentration out has to be below, or it cannot exceed 20 milligram per liter. Okay, so it has to be below this value here. And assume that this is well mixed and there are no losses or gains of water other than the sewage input, right? It's just saying that there are no other input or outputs, right? So it's asking us, what is the reaction rate or the reaction rate coefficient, which is a K, it must be achieved for the, in order to let the concentration to be below 20, right? So let's say if the rate coefficient is too small, basically means that the organic contaminants are not being degraded, then what people can do is we can add in more bacteria inside, or we can raise the temperature to let the reaction happen more quickly, right? So given all of these conditions, since this is a CSTR, right? So we know that C out is equal to C in divided by 1 plus K theta, right? So we can directly list all of these conditions out. And we know that this concentration has to be below 20 milligram per liter. Okay, so we can also plug in this value here. We know that this is 100 milligram per liter. This is a C in, right? So what this means is that 1 plus K theta has to be larger than 5. Okay, so K theta has to be larger than 4. All right, so what this also means is that K has to be larger than 4 divided by theta, right? So this is asking what is the biodegradation reaction rate coefficient must be achieved, right? So this is basically give you the minimum reaction rate constant for this small pond here, right? So now it's just a matter of solving for theta, right? So the theta is equal to V divided by Q, right? So V, since we have the surface area, is equal to 10 hectares, right? We have the depth is equal to 1 meter, right? So we know that volume is equal to 10 to the, basically 10 multiplied by 10,000 multiplied by 1, right? So this is the total volume. And then the flow rate is equal to 8640 meters cubed per day. This is meters cubed. So basically you can plug in all of these conditions and then try to solve what is the theta, right? And then this will give you the final answer or the minimum reaction rate constant that needs to be achieved for the CSTR, right? So this is the CSTR. So I think we just have 5 minutes left and we should basically jump in this, the final reactor type, the PFR, okay? So the PFR looks a little bit different compared to the CSTR or batch reactor. So you can think of the PFR as a very long tube. So what happens is you have this tube here where you introduce the influent, let's say the contaminated water, the wastewater, and then within this tube here, you have the reaction that's taking place like a plug. Okay, so basically, you can think of a thin slice here. That the reaction is only taking place within this thin slice. Okay, so there's no mixing across the, no mixing along the flow direction, but there's only mixing across this flow direction. Okay, so everything within this thin slice here is well mixed. Okay, so if you just follow thin slice here, then at the beginning, it has a high concentration of the pollutant, right? And as time goes on, the reactant is concentration is reduced because of the react. And then finally, at the end of the tube, we have these organics concentration further reduced. Okay, so again, we're quite interested in how it performs, right? Basically, we want to solve for what is the salt. I've done this for reactor, CSTR, about this PFR. So what we can do again is identify this control volume. Okay, so for the PFR, we also assume that it is under state. So the state condition will give us the result that in minus out minus reaction is equal to 0. Okay, so what this also means is that basically C in, Q in, minus C out, Q out, minus the reaction term, the K C multiplied by V is equal to 0. It is quite similar to the CSTR, except that the C here within the entire reactor is not a constant, right? We know that the concentration is going to decrease, right? At the beginning, the concentration is highest. At the end, the concentration is going to be the lowest. So we cannot make any assumption to this concentration here, right? So instead, what we can do is we can just pick a very thin slice, as we have introduced earlier, right? Let's say that we're interested in this thin slice here, right? For this one, we can assume that this location here is X, and here the location is X plus delta X, right? X plus dx. So what we can have is the flow rate multiplied by the concentration of Cx, right? This is the in, minus the flow rate multiplied by Cx plus dx, right? We know that the flow rate is again the same, right? There's no other other inlet or outlet for the flow. The flow has to be the same as before, which is Q, right? And then we need to we need to deduct the reaction term, which is R multiplied by dV, which is a very thin control volume here, right? So further, how do we solve it? So what we can do is we can just look at this dV here. So dV is just the volume, like the small volume within this slice. So we know that the dV can be calculated by the surface area of this tube multiplied by dx. Okay. So further, we know that the flow rate is calculated by S multiplied by velocity. Okay, so the velocity is basically how fast the wastewater moves within this tube, right? And if you multiply this velocity by S, or the surface area, you're going to get the flow rate, okay? So what this means is that the S is going to be equal to Q divided by V, right? So we can convert this term into Q dx divided by V. And further, you know that dx divided by V is going to be equal to dt, right? A small section of the distance divided by the velocity is going to be a small section in time, right? So then basically we convert this dV term into Q dt term. So now if you plug in back into this equation, right, so we can write out the equation here. So Q Cx minus Q Cx plus delta X is equal to R Q dt, right? So you can cancel all of these Q terms here, right? And then what happens is basically you have dC dt equal to R, which is equal to Kc. Okay. So this looks pretty familiar. This is basically the equation for a batch reactor, right? So the concentration, basically what you have is the concentration at the outlet of this reactor is going to be the concentration at the inlet of the reactor multiplied by minus Kt. Right, so further we can solve for this T here. T is going to be equal to V divided by Q, the same as the characteristic time that we defined for the CSTR. Okay, so basically you can see that the PFR, although it looks different compared to the batch reactor, the CSTR, it actually has the same performance compared to the batch reactor. And further, you can do some practice regarding the performance of the PFR. So I have a discussion problem regarding the reaction performance. So maybe we can go over this in our next class. So this is the final probably the final piece for the mass balance. So in your homework, I think there are also maybe one problem regarding the performance of the PFR, right? So that's it for this class, and I'll see you next week.
Dr. Wang,
Yes?
can I see the answer to the second example again?
What's it? The answer for what?
Can I see the answer for the second example?
Let me see. Yeah, I didn't. Oh, yeah. So here is the answer.
Okay.
Yeah. So actually, if you have the textbook, so this is the. I just did a screenshot for this problem from the textbook.
How are you able to calculate theta?
Oh, the theta?
Yeah.
Yeah, so the theta is the characteristic time, right? So this time is, if you remember here, we did a substitution. So the time is equal to V divided by Q. So V is the volume of the reactor, Q is the flow rate, right? So for this problem, it provides you the basically the geometry for this pond and also the flow rate for this pond. So you can do that calculation to find out this time.
How are you given the volume though? Because it only gave you the surface area.
So you see the surface area and depths, right?
Yeah, okay, I see it now. Yeah, thank you.
Yep.